Hello, everybody. My name is Theo Mahaffey. My mentor this summer was Michael Ochoa, and I'm going to be telling you about the work I was doing this summer on spectral Hamiltonian learning in silicon phosphorus arrays. So for starters, I want to explain what these arrays are. So experimentalists at NIST, they take a flat layer of silicon that's coated with hydrogen atoms, and then they can use scanning tunneling microscopy to pick off the hydrogen atoms at select sites on the lattice, which then leaves open sites for a phosphine gas to bind to in the top right picture there, which then once more silicon is layered on top, we are left with a chunk of silicon that has phosphorus atoms placed exactly in the sites that we would like them to be. So why are they working to build these devices? The answer is analog quantum simulation, which is effectively a near-term application of quantum information systems by which we can realize a quantum system in the lab at a scale that would be impossible to simulate on a classical computer. There are lots of different methods to do this because there are lots of different quantum systems that scientists are studying. We have Rydberg atoms, trapped ions, superconducting qubits, and many others, including solid state devices with impurities like the ones I'm telling you about. So I want to explain this diagram just a little bit. I'm not going to go into detail on the graphs, but I just want to show that these orange images are actual scanning tunneling microscope images of these devices. So each of these clusters in this 3x3 grid is a cluster of phosphorus atoms within the silicon lattice. And then by varying the potential across these gates on either side, we can measure how electrons transport themselves through these arrays. So we're looking at how the electrons are tunneling between the sites in this lattice. Now, the physics that we are trying to explain with these devices is the Hubbard model, which is a very general way of constructing a Hamiltonian for electrons in a lattice. And the key kind of feature of the Hubbard model is that we are talking about the electrons as occupying discrete sites. And when they do, they have a certain amount of energy that we call epsilon when they are on a site. And they also have a tendency to tunnel between neighboring sites that we ascribe an energy T. I want to point out that the T shown in these images is only for nearest neighbor tunneling, but you could also conceive of tunneling between, say, the diagonals of these little squares or other combinations of impurities that would each then have their own tunneling energy. Another important thing for my work is that I'm only looking at single electron states, so we don't have to worry about the complicating effects of spin, the up and down arrows here, nor do we have to worry about this repulsion term U that happens when two electrons are on the same site. The other background physics to go over is band theory. So if we look at this image here, it's the band structure of silicon, where the black curves show the available states for electrons in the silicon lattice. And you can see that the lower energy states in the valence band are separated from the higher energy states in the conduction band by what looks like that white ribbon going across the graph. And if we look at the maximum energy in the valence band and the minimum energy in the conduction band, they are separated by what's called the band gap. And that is the amount of energy that an electron would need to excite to go from a valence band state to a conducting state. But what happens when we introduce these phosphorus atoms into the lattice is we create states in the middle of the band gap. And instead of just creating one state, we actually create 6 due to the Valley degeneracy in bulk silicon, which is just a detail that tells us we have more states and more properties to determine about these systems. The other key part is that because we have precise control over where we put the phosphorus atoms, we have precise control over the properties of these states. So it's been my job this summer to figure out what those properties are via a technique called spectral analysis. So I start with some calculations that my mentor did of the energies of these available states and their wave function overlaps that were done with atomistic type binding codes. And with these calculations, I'm able to simulate the time domain dynamics of an electron. So if we take an electron and we started at one site in the system, we can look at the probability over time that it returns to that site. And we see some sort of oscillation here in this example case I'm showing. Then I can take the Fourier transform of this to get the results in frequency space, which is the red graph down here. And then I could do some math on the side to connect the peaks in the frequency domain to the differences between the eigenvalues of the Hubbard model Hamiltonian. So in this example, for the 2-level system, we have this Hamiltonian, which is a matrix that describes the behavior of the system. We get the energies, and we look at the difference between them. That's 2T, and that connects to the frequency of this peak at 2 millielectron volts. So that's the basic gist. As we look at more impurities, we have to deal with more energies and more peaks, but the same idea applies. So let's look at the systems that I'm actually working with. We have the 2-particle system where we have 2 phosphorus atoms in a line, and we can look at the tunneling energy between the impurities. We have the 3-particle system where, again, we have nearest neighbor tunneling, but we also have this lambda term, the on-site shift, that I need to explain a little bit. So like I said, we have the energy of the electron on a certain site, but then when we introduce other phosphorus atoms into the lattice, those come with a Coulomb potential that's going to affect the energies of the electrons on the other sites. So due to the symmetry of this system, we have one shift lambda O on the outer impurities and another shift lambda I on the inner impurity that's going to be larger because it's closer to both of the other impurities. In the 4-particle case, we have a square where we can look at nearest neighbor tunneling along the edges of the square, as well as tunneling through the diagonal. And in the 5-particle system, which is like the 5 on a dice, we have the nearest neighbor tunneling with the central impurity, the tunneling along the edges of the square. And again, we have 2 different on-site shift terms that we can worry about. So let's look at the results for these systems. In all of these graphs, the horizontal axis is going to be the spacing between the impurities. So if we take whatever geometry is shown in the schematic that I just explained, and then we space them out farther, how do these properties change? So for the 2-particle system, we see that the tunneling energy decreases exponentially with the distance, which is what we would expect. In the 3-particle system, we get, again, an exponential looking decrease in the tunneling. And we also, like I said, we can get the difference between the on-site shifts. That's the way the math works out. We can see how much larger lambda I is than lambda O. And I also have some other values up here, which are calculations that were previously done by Michael via a different method. And we see a good agreement, which is good news for this method. And even better news for the group is that this spectral analysis can get us information at closer separations than we could by just looking at the wave function overlaps, which is what was being done previously. For the 4-particle system, like I said, we get both of these tunnelings. And the interesting thing for this case is that the diagonal tunneling beta in the lower graph is actually larger than the nearest neighbor tunneling in most of the cases, which is a pretty cool physical effect. If you want to find out more, come find me in the poster session. And in the 5-particle system, we again see that the tunneling across the larger distance is actually ascribed more energy. That's the blue line here compared to beta being the red squares. And again, we can get the difference between the on-site shifts, just like in the 3-particle case. So we have all these results. What do they mean? For starters, we know that this method works because we have good agreement with the 2-particle and 3-particle results from previous methods that we've accepted. But we also have the benefit of being able to look at closer separations. The 5-particle results are completely new, which raises fun physical questions like why is the nearest neighbor tunneling always smaller than the tunneling through the edges of the square? I've also been working on a different method to perform this analysis that automates certain parts called direct Hamiltonian optimization. And with this method, we already have 2-particle results that agree well. So that bodes well as we scale up to the more complicated systems. And finally, the experimentalists in the group have been working hard to perfect their placement of the dopants, getting them exactly where they want in the numbers that they want, which is going to allow them to create larger and larger arrays like 5x5 squares and 7x7 squares that will exhibit more interesting and novel physics. So thank you for listening to me. I also want to thank my mentor, Michael Ochoa, and Daniel Serrano for organizing this program.